video. So this is kind of a detective work lab. We have 4 unknown compounds. They all contain copper, and we have to figure out which one's which. And it's a kind of a 2-part lab. The first part is to use spectrophotometry to figure out the amount of copper that's in these unknown samples. And first we need a calibration curve, so we produce a standard curve of known concentrations of copper, and then compare that to the absorbance of our solutions of our unknown copper solutions. So from there, you can get a percent by mass of copper for each of your compounds, and then compare that to your percent by mass of copper that you can calculate, and you did calculate in your pre-lab for the 4 possible copper compounds. So your 4 possible compounds are listed on this first page here. You can calculate the percent by mass, the mass of copper over the total. Now be careful and make sure that when you calculate your total mass of these compounds that you include the waters of hydration. Once you are able to run the samples and get and calculate your percent by mass of copper, you'll be able to distinguish, should be able to distinguish 2 of these 4 compounds, and you'll know which one's which because their percents are quite different from each other. But 2 are a little bit close, usually a little bit too close to be sure which one's which. So we need more information. And part 2 of this lab reacts or introduces water to these 4 compounds and nitric acid as well as barium nitrate. So you can take these 4 compounds and on paper react them with these 3 substances and determine what you should be able to see. Do I expect to see bubbles? So is it a gas forming reaction and I should see bubbles? Is it a precipitation reaction where I would expect to see a precipitate, etc.? And then from there, you can use that information to determine which of the last 2 are which. So let's get to it. And we're going to start by making our standard curve, our standard copper containing solutions. So these are of known concentration, and we are going to put them into a spectrophotometer, which you've done before. And the amount of light that is absorbed at a certain wavelength correlates to the amount of copper that's in that solution. So what we've done is we've made a solution of known concentration, which was 0.01501 molar, if you didn't catch that. So that was our standard 4 concentration. And we did that by measuring out a known mass of copper nitrate, trihydrate, and put it into our flask and brought it up to the line. From there, you can see that 4 milliliters of that most concentrated standard number 4, was transferred into this tiny little cute volumetric flask that holds 10 milliliters. It was brought up to the line, so that flask was containing exactly 10 milliliters, and now that's our standard 2. Similarly, we did that with 7 milliliters of our concentrated solution and made standard number 3. So now we have standard number 1 has 0 copper in it, it's just nitric acid. We have standard 2 and 3, which have concentrations between the most concentrated and nothing. So we have 4 different known concentrations. You have to calculate the molarity of the other 2, which is why I'm not telling you those. And then you have 4 known concentrations. We'll put them into the spectrophotometer and we will get their absorbance and create a curve. So let me play this on. So we used an autopipetter to do this transfer of the most concentrated standard 4. So this is just showing how we made the other standards. And what we did was put them into, I say we, thank you, Mr. Davis, for doing this video for me. He put these into these are called cuvettes, and these are sample holding vessels that can go into the spectrophotometer. They don't absorb light or reflect it very much. So what we're doing now is telling the instrument, this is something that contains no copper, and we're going to say, okay, this is 0. Even if it is absorbing a little bit of light, call that 0. So the difference, or anything that is absorbed beyond that, is due to the copper. So we've done the 1, and we're at a 0, 0 absorbance. So now we can just put the other samples into the machine, the instrument, and get the absorbance of each. So we're just recording those. The absorbances for the standard solutions are, just going to pause this. I can pause it on the sheet. So the first sample is 0.000. That's given for you. So we zero the instrument and we got that. Sample 2 is 0.727. Standard number 3 is 1.200. And standard number 4 is 1.750. Here's a look at our sample. So this is the first time you're looking at A, B, C, and D. And I want you to write down the color and the masses of these samples as you go through here. 0.1581, you can record what that looks like, 0.1530, and 0.1547. So there they all are. You have to record the color and the mass in that table there, and then these will be worked up and we'll have an absorbance as well. And I want to show you this one next. So here we are making our samples. We're going to do an analytical transfer. That means all of the material that is in that weighboat is going to go into the flask. Dissolving these up with nitric acid. And making a solution, so all 4 of these will be made the same way. Put nitric acid in our flask and we will bring that up to the line and mix it well. The same thing that we did with the standard samples, we are going to do with the unknown samples. So we're going to mix these up and put them into cuvettes and then record the absorbance from the spectrophotometer. And I want to show you about here. So here's all of our solutions. Notice and take observations of what these solutions look like. And it's interesting that they're all pale blue, right? That's the copper. So all of these solutions liberated copper ions into the solution, and that's what the spectrophotometer is picking up on, okay? So that copper is absorbing the light of the certain wavelength, and since it's absorbing it, the detector on the other side is not picking up that light. So it knows how much light was shining through the sample, and then the sample absorbs a certain amount, and it also can read and detect how much light came through the sample. And the difference between those two is how much was absorbed. And the amount of absorbance is directly related to the concentration of that ion, the copper ion in solution. So let's see. We're going to fill our cuvettes and then read them. So we're putting A into the cuvettes. And then we're going to read them. And I'll show you that. I know I showed you before with the samples, but it's kind of nice to see. So we have C, recapping. And D. If you can hear a noise in the background, that is Professor Corey with a chainsaw. He probably thought I was done with this recording by now. Here's our spectrophotometer. We need heat though, so he's got to get out there and get us some more wood. Same thing, we've already zeroed our machine, our instrument, and we can record the absorbances from there. And I'm just going to pause this and give you the absorbances. So absorbance for A is 0.667. Absorbance for B is 1.42. Absorbance for C is 0.584. And absorbance for D is 1.035. Okay, and we have 4 minutes left in this video, so let's see if we can finish it up. Oh, here we go with the absorbances. So there's the 0.667, and I just read you those. All right, so here's part 2. We are doing our reactions with water, nitric acid, and barium nitrate. And this first part is really just kind of looking at these samples. You can make observations, and the way this is set up, we have a well plate here, so we can do small reactions, qualitative reactions. We're not measuring the amounts of any of these things, but we have A, B, C, and D in all of these well spots, and going across, we're going to react them with the different items. So we're going to mix them with water first and see if all of them are soluble or not. And you have to mix them all up and see if they dissolve. Now, if they dissolve, it should create a clear, transparent solution. If it does not dissolve, then it will stay cloudy. It might look reasonably homogeneous when you mix it, but if you let it settle out, if it doesn't dissolve, then it will still be cloudy and it'll kind of settle out to the bottom. And at the end, we're really going to be able to see all of these, the results of all of these. So I don't want to necessarily waste all the time that I have left. But you can see A is certainly dissolved. B still looks cloudy to me. That looks cloudy. C looks like it's dissolving up quite nicely. Nice and clear solution, not cloudy at all. We have to change our stir rods in between so we don't contaminate. So 3 have dissolved. B is the only one that didn't dissolve. And we're adding nitric acid. Nope, we're dissolving all of the rest of them in water. So we start out by dissolving them in water, so we have an aqueous solution. Of course, B isn't dissolved completely. And now once we dissolve them, we're adding in this case, nitric acid, and then we'll add barium nitrate to the other. I'm going to jump ahead to this image right here. Right there. Pause. Okay, so with our nitric acid, you can see we've got no reaction A, no reaction C or D, but boy, look at those bubbles. Look at the bubbles with B. And then the reaction with the barium nitrate, we have a clear solution here for A. B is cloudy. C is cloudy. We've got kind of a greenish cloudy for B. We have a whitish cloudy for C, and then just a clear